Good afternoon, everybody. First, I would like to just remind you about our upcoming midterm one, 1 week from today. That's Tuesday next week, March 9th. So it will be available on Blackboard for 24 hours on March 9th from midnight to the end of the day. And you can choose any 2-hour period to start the exam. So once you start, it's going to start recording time. So you cannot pause and come back. You have to finish it in 1-2-hour setting. And it has 20 choices, 20 questions, either conceptual question or with calculations that you have to enter numerical answers. And the lecture, the practice exam is already uploaded along with the solution. So I encourage you to try to work it out yourself before looking at the solutions. We will not host a lecture. Would I still be here? Someone asked at this time at class hours. Yes, I will still be here. So if you do want to ask me questions, feel free to log in, but you're not required to. And of course, you're welcome to come to my office hours this week and Wednesday and Thursday. Would I be able to say if you understand the study guide, you are good for the exam? Now, the thing about physics is it's solving problems. It's like you have to understand something that then you will be able to apply it. It's not like taking maybe this is not an appropriate example. An introductory biology exam probably have a lot of you have to memorize a lot of things. So I give you a list of things that you need to memorize, and you did memorize, and I'll say yes, you're good for the exam. Now physics is not like that. It's not about memorizing something, it's about applying something. So I would say this is my recommendation for preparing for the exam. I'll go through the topic we went through one by one. I say start with, okay, 1D kinematics. I wanted to understand, first of all, look at the lecture notes, understand the concepts, and then try to find a few problems on that topic and to solve it on your own without looking at the solutions. You do a few of those, you feel really good, and you move on to the next topic, say projectile motion, 2D, right? 2D motion, and find a few problems on that and work it out. And then move on. So that way you're giving yourself the chance to practice before you actually go to the battlefield to do the actual task. So this is what I mean, right? It's more like, I will compare this exam more like you try to learn a sport or riding a bike or some other technique, right? You have to do it yourself and know how to do it, then you'll be able to perform on the exams. But on the good side is that it is open notes and open book, so that does take some pressure off, that you don't have to memorize all the equations, it's there, but it's also still good to try to organize your knowledge on your own so that when you need to find it, at least you know where to look for. Okay, all right, so that's just a heads up of what's coming next week. Today, we will continue to do one more example on applying Newton's second law, and we will do our discussion on Newton's third law. Now, there's a follow-up question on whether all the question types are in the study guide. Now, depending on what you mean by question type, for example, if you group question by their surface features, as a lot of as we were novices, we come to physics problems thinking, oh, this problem involves a ramp. That problem has a ramp in it. So they're similar, but they could be very different problems, right? They can be totally different. So I would group questions by the physics principles that are involved. So yes, in that sense, the practice exams are about all the content we are going to cover. 2D motion, Newton's second law, 1D kinematics, Newton's first law, all of that. In the sense that I would say, yes, the question types are similar, even though one is a ramp, the other is a tension and the force. But if they all involve Newton's second law, the process is the same. Okay. All right, let's take a look at this question. Here's an example. I want to give you a couple minutes to read it. And first of all, I want you to try to draw the free body diagram, label the forces on the car. Okay, so you don't have to go to your breakout room. Just look at a question here, and you can try to draw the free body diagram. And then we'll talk about it together, and we will solve this problem together. Okay, couple minutes. You can go ahead and try to read the problem on your own. So the first two questions, one is asking about the normal force on the car. The second question is asking the kinetic friction on the car. Okay, there are question 3 and 4 as well. 3 and 4 has to do with kinematics. Remember, these type of problems are examples of questions that require both the forces and the kinematics equation. So you need dynamics, the Newton's second law, as well as what we did in the first chapter about the kinematics. How far did the car travel to a stop? That's question that's being asked in question 4. Okay, so hopefully you have managed to draw the free body diagram of the car, and let's take a look at this together. Okay, so this is a car. Now let's draw the free body diagram together, and let's label all the forces that's acting on the car. Would anybody be able to tell us the forces that is acting on the car?
Normal force, frictional force.
Normal force, very good. In this direction, right?
Gravity.
Vertical to the ramp. Friction, and in which way the friction is pointing at?
Down.
So the car is, let's see which way the car is going. The car is sliding down. So the car is going down. So friction is, kinetic friction is opposite to the motion, right? Yes, so as someone typed in the chat, is going to be up the hill. I'm gonna call this friction kinetic friction, F of K. And I also have normal force of gravity, I'm sorry, gravity here of G. Okay, I think I labeled all the forces now. And let's also define our positive X and positive Y. So I'm going to label this direction as the Y direction. So the normal force is in the positive Y direction. And I could label downward as my acceleration, or I could label upward as my positive X. So it doesn't matter, it's up to you how you want to label this. So I'm gonna say up the hill is positive X. Okay, so it's not quite parallel. It's going to be parallel to the ramp as positive X. Okay, all right, so let's look at our first question. First question is, what is the magnitude of the normal force acting on the car? Anybody are able to just shout that out, and you're very familiar with this?
force equals mass.
I'm sorry. I'm sorry, I didn't get that. mg cosine, okay. Yes, mg cosine of theta, excellent. So the normal force is canceling out this component of gravity. So for gravity, once you have found gravity, usually people decompose it into two components. It's a f of g in the y direction and f of g in the x direction. So this is theta. I'm sorry, this is not a very good drawing. I want to redo this. Okay, so FGY and FGX, this is theta, and this is theta. Okay, so if you still don't know how to get the component of gravity on the ramp, you need to go back and review after class. Make sure you do understand how to do that, because that will come up over and over again. Now, if you don't know how to do that after you review, you should ask me, okay? Okay, so if you look at what is in the y direction, the normal force is balance out this component of gravity. This is an application of Newton's second law in the y direction, because there's no acceleration in y. So all the force should cancel out. Normal force is equal to the y component gravity, which is gravity times cosine of theta, which is mg times cosine of theta. So that's it. Question 2, what is the magnitude of the kinetic friction on the car? For kinetic friction, we know that there is a formula that kinetic friction is the coefficient times normal force. Okay, so right away you know that it's going to be this times normal force you just got as mg cosine theta. So that is your friction. You're done. The first two questions pretty straightforward. The third one is asking, well, what is the magnitude and the acceleration, magnitude and direction of the acceleration? Okay, so we want to solve for the acceleration. Now the car is sliding down. The car is going down. In which way is the acceleration? Is the acceleration pointing up or pointing down? What do you think? Let's read the question to see if we can figure it out. The car sliding down to a stop. So from the sentence, can you figure out in what direction the acceleration is pointing at? If the acceleration is pointing down, the car is also sliding down. Do you think the car will ever come to a stop? It will go faster and faster downhill, right? Because the acceleration is in the same direction as your initial velocity. It's going to make you speed up and more. But the fact it's sliding down to a stop, what does it imply about the direction of the acceleration? I know it's intuitive to think it's down because the car is going down, but it's going down, but it's slowing down, right? It's sliding down to a stop. So the car is actually slowing down, even though it is going downhill. So do you agree that the acceleration has to be up the hill? Anybody disagree with that? Now, if you disagree, you should let me know, because it implies there's something we don't understand, we have to address it. So acceleration is along the ramp upward. Okay, so I want to calculate this acceleration. Now remember, when solving physics problems, we draw a picture, we label the quantities, we need a question, now we have a question. Now we need to think about what physics is involved, right? So what is the physics principle we're going to use to solve for acceleration? Are we using
Kinematics.
Kinematics? If I need kinematics, I need something like velocity, distance. I don't really have that information yet. I do have something about the forces, yes. So I could use Newton's second law, very good. Second law. So F net equals ma that is Newton's second law, is the physics I'm going to use here. And let's apply it in X direction because the car is going in that direction. So all the forces in the X direction, if you look at it, there are two forces in that direction, right? Yeah. One is kinetic friction minus the component of gravity. I put kinematics as a positive force because I defined upward to be positive. That's just how I defined it. You don't have to do it that way. Right? Positive, this is positive, and this is negative. Because MA is also positive. Okay. Now this is you already got this. Let's plug it in. Mu k mg cosine theta minus f of g's of x. Again, that should be something that comes really quick to you. Anybody would like to shout out what fgx is? The x component of gravity is sine theta. Yes, very good. Mg sine theta. Thank you. It's mg sine theta equals ma. I'm gonna cancel my m. You can see a lot of times I don't really need all those quantities. You can give me the mass, but in this case, I don't even need it because my acceleration is equal to mu k t cosine theta minus g sine theta. And that's it. Sometimes you can take g outside of the parentheses and write it like this. That's okay, fine. That's okay. Okay, so you can calculate this acceleration. Now at this step, I do like to plug in some numbers because I need to know the magnitude, right? So I need to answer that question. So let's plug in the numbers. G is the constant 9.8 meters per second square. Use of K is given, what is use of K in 0.1. Okay, so 0.1 cosine of, is there an angle? 5 degrees only, so it's a very small ramp. Okay, 5 degrees minus sine of 5 degrees. So plug that in, you get acceleration as in 0.125, so really small.
Are you gonna do something both in class?
No, I think we're doing something else.
Huh?
I think she's doing something else.
Question 4, how far does a car take to slide to a stop? So question 4 is asking, okay, so the car is here and then stop somewhere here, right? I'm looking for the distance.
Don't bother him.
So I need to find out what physics is applicable here. So anybody would like to say what kind of physics should I use to find the distance of the travel?
Kinematics.
Kinematics, very good. Okay, so I need kinematics of 1D motion. Do I need a constant? There are two kinds of kinematics equations, right? One is constant velocity, one is constant acceleration. Which one should I use?
Constant acceleration.
Yes, constant acceleration, because we just calculated this is a constant acceleration. So this one. Okay, so constant acceleration, I want to find some information about the displacement. Okay, remember there are 3 equations in kinematics. I'm gonna write it out again. You recall we have these equations, we have this equation. V initial is just V naught. I'm just gonna say V naught so you don't get confused when I mean V naught. And we have another equation. So which of these equations do you think I should use to find the change in, so this is xf minus xi actually. The last one, yes, the last one would be the one that we need to use. And let's think about this, okay? In this case, we have defined upward to be the positive direction. So if I'm, okay, so I'm going to draw a graph here again, right away. So X, so you go from here, let's say you travel from here, XF to XI. Okay, so in my particular diagram, XF is indeed larger than XI. So I get XF minus XI is going to be the positive value. Good, that is what I want because I want a distance. So here, let's say I'm just going to call this the change in X is 2A times V final minus V initial. Let me see. So you'll find the change in X will be whatever the initial velocity is, the initial speed of 10 meters per second with initial velocity divided by the acceleration, which is 0.1225. So distance is the change in displacement, and I will get a number of 408 meters. So you say the car will travel 408 meters before it comes to a stop. So it'll be here. How far is 408 meters? So we can see the combination of dynamics and kinematics together is you use Newton's second law to get acceleration and then connect that to your kinematics quantities. Now, sometimes vice versa, you use kinematics equations to get some information about acceleration, and you go back to get some information about the forces. So you can see how these two topics can be connected together through acceleration. That's the quantity that connects the forces to the other kinematics quantities. All right, so we need to talk about Newton's third law today. That's what we are going to discuss next. Newton's third law is actually probably something you have already experienced in your life. So it will be quite intuitive. Newton's third law is simply saying is, I'm going to say it in everyday language, is if I push you, then you push me back. So that's Newton's third law. That is saying if a force exerted by body or object A on object B, then there must be a force that is equal in magnitude, the same amount, but opposite in direction by object B on object A. So even if you are actively pushing the wall, let's say you put your hand on the wall, you exert a force on the wall, even you are the one who seems to be initiating this force, but at the same time you're pushing the wall is pushing back on you with the same amount of forces, but opposite in direction. So this is Newton's third law. The force A on B is negative, which means opposite directions, right? So that's why it's negative. The opposite direction of force B on A. We call these two forces an action and reaction pair. So whenever there's an action, there's a reaction. They always act on different objects. So, right, because the force I push on the wall is acting on the wall, but when the wall pushing back on me is acting on me. So the action-reaction pair, be very careful about the action-reaction pair is not the same as when you have a pair of forces canceling out on one object, right? If you are standing on the ground, your gravity and the normal force cancels out. These are different. These are two forces acting on the same object, on you. Where this action-reaction pair are on two different objects. We will continue to look at it to be a little bit more certain. So let's look at this demo really quick. Open it up.
Right.
Let's see.
Not that easy, but Grammarly can help. This sentence is grammatically correct.
Okay. All right. So looking at the let's I'm just gonna start with the very first one. So here you see that once you open up the fan, the car starts moving. Can anybody explain this using Newton's third law? It seems so straightforward. Like, of course, the car is going to start moving. But can you explain this using Newton's third law?
Since the fan can't push the air behind it,
Uh-huh.
the fan can't propel the mass of the vehicle forward.
Okay. So the air is being pushed one way, right? Propels the air one way, and that's the force acting from the fan to the air. So you're saying, okay, if we use Newton's third law, the action-reaction pair, then the air must be pushing back on the fan, right? Pushing back on the fan in the opposite direction, so that air pushing the fan forward. So the fan pushed air backward, the air pushed the fan forward. So the fan would push the air in what direction? The way you're looking is it to your left-hand side, or is the air going right-hand side?
The air is being pushed to the right-hand side.
Okay, so we predict the fan would be going left, right? Opposite to where the air is going. So was that the case?
Yes.
Yes. And now they have attached a piece of plastic onto this thing. And once they attach this and you turn the air on, the fan on, well, of course, this is just him pushing the whole object forward. But then now you use the fan. Somehow that make it different. It's no longer moving, right? So what is happening here? Why is the cart not moving? What do you think?
Now the force that is being pushed into the air is then colliding with the flat plane, which provides an equal and opposite force, so that the net force is 0.
So equal and opposite force. Yes, okay, so I say the air is now, okay, let's be very clear. We're still looking at all the forces on the cart, right? Because we're interested in the motion of the cart. So we just said the air is pushing the fan to the left-hand side. Very good, because that's the action-reaction pair from the fan to the air. But now the air is also hitting the board to the right. So that's what you mean by they cancel out, right? The air that is pushing the fan to the left and the air that is hitting the board to the right. These two forces cancel and they no longer move. Another way to look at this is by looking at all the fan, the air in between, and the board to be the entire system. Think about you kind of enclose everything into one closed box. So if they are part of the same system, you don't look at what's going on between the fan and the air and the board, because those are internal forces. It's like you use your left hand to push yourself. You're not going to be able to push yourself forward because that force is internal force that cannot change your status of the motion. So if we enclose everything, then they look like a one complete object, and their internal forces are not going to move. But that's a side note. All right, let's go back to our discussion. We want to say, remember at the beginning of class, we said we will be able to explain some of this phenomenon using physics. So how does a rocket work? At this point, we could give a simple explanation using Newton's third law by saying rocket ship exert a force on gas particles by pushing them out in the back. So by Newton's third law, the gas will in return push back on the rocket upward, right? So you push the gas down, the gas will push the rocket up. So the rocket launches. The question is, do you think these rockets will require air to accelerate? So do they still works in space?
They still work in space because it's being forced. The gas is being stored inside of the rocket and then forced out to create the propulsion force.
Yes, very good. Thank you. It's not the air that's around you, it's the air that you carry with you. So it's the fuel that the rockets carry. It's okay. It still works in vacuum. Okay, now let's look at a few of these questions. Help us further gather the idea about Newton's third law. So we have two people, one with a very small mass, one is a very big mass. They move with the same speed and they collide head on. Which person experienced a larger force? When I say average, meaning that, well, during the collision, there are some instances might be bigger forces than the other, but on average, do you think which person experienced a larger force? The smaller guy or the big guy, or both the same? Or do you want to have more information? I'm gonna let you go ahead and vote. Okay, I gathered most of the votes already, so another 5 more seconds. Okay, I'm gonna go ahead and close the poll and we can take a look. This is our results, all right? Seems other than C, the next majority will be the A. The small guy experienced a larger force. It seems intuitive, right? Because if something this really happens, we feel like the smaller guy will have more damage on this person, or it will experience more of the effect of the collision. But C says they both have the same force. So if we use Newton's third law, then viewing that, okay, if I push on you and you must push on me with the same exact force, so that seems to suggest that C is correct answer. But that is a little bit conflicting with our intuition. So I'm going to follow up with another question. And hopefully after that question, we will be able to consolidate some of these confusions. So the next question is, which of the person will experience a larger acceleration during the collision? Okay, so again, I will let you vote. Same question, but I'm not asking the force now, I'm asking the acceleration. Okay, any last minute vote? 5 more seconds. Okay, let's take a look at this together. I'm gonna go ahead and close the pool. This is, we kind of have our answer reversed, right? All right, so if using Newton's third law, we're saying the forces, well, of course, each of them will have gravity, right, and normal force acting on them, but those two are balanced out. What is interesting is the forces in the horizontal direction, right? So the only force that exerting on them is the force from the other person. So for example, for this little guy, you'll have a force from the big guy to small guy, right? And on the big guy, you'll have a force from small guy to big guy on the other opposite direction. So we're looking at due to this force, how does the acceleration compare? And again, how does acceleration relate to forces? The acceleration of the small guy is going to be the net force divided by the mass of the small guy, right? The acceleration for the big guy is going to be this force divided by the mass of the small guy and mass of the big guy. They can have the same force, but the small guy have a smaller mass, so it's going to have a much bigger acceleration, right? So A is correct. Now the previous question, yes, they do experience the same amount of force, but one of them will experience a much larger acceleration due to the smaller mass they have. So you can say, if there's a bug hitting a car, they do exert the same amount of force on each other, but that force will be so damaging to the bug that barely made any dent on the car, right? Because of the cars is so big, that same force is not going to have the same influence, so that we are able to resolve the conflict with our intuition. So again, it's direct application of Newton's third law. Now, recall, we had talked about the elevator question by asking what is the reading of the elevator. Previously, we simply said the measured weight is equal to the amount of normal force acting on the person. Now we're able to explain why. Okay, why are you measuring the normal force? So by looking at the person and the scale separately, what is happening to the person is the scale is providing a normal force upward, right? And this is the action-reaction pair. This is Newton's third law pair. Now, if the scale push the person upward, then the person must be pushing the scale back in the same and opposite direction, same magnitude but opposite direction. Now you're pushing the scale, pushing down on the scale, and that reflects in the reading. The scale picks up on that force and have that reading. So whatever reading you get is actually reflected by the normal force you receive. So that's why previously we had made that assumption. So it already used the Newton's third law in there. Okay, now let's look at this particular question with multiple objects, because there are a lot of action-reaction pairs. There are a lot of pair of objects. So first of all, the first question is, what is the free body diagram for the book A? And then we are going to draw all the free body diagrams for all the books. And we will be able to point out which of these forces are in Newton's third law pair. They are an action-reaction pair. So I'll let you go ahead and actually discuss this for a couple minutes within your group, okay? You can take a screenshot before you go to the breakout rooms. Okay, 15 more seconds. So if you haven't voted already, please put in your vote. Okay, all right, let's take a look at this together. Any last minute vote? Okay, I'm gonna go ahead and close this. So this is our results. The unpopular answer would be A, 3 forces down, 1 upward. The next popular one is D, 1 force down, 1 upward. They cancel out. I'm glad that, we know that A is in static equilibrium, so the forces better cancel out. And the length of the arrow kind of reflect that. And there are some choices for C and E and B as well. Okay, so remember when we talk about free body diagram, we think about this object, right? We're curious about A, isolate the object in the sense that we focus on A. And we think about in what other objects it is in contact with, it is touching. So why don't we start with the forces one by one? So I'm gonna label the obvious ones and you guys can add other ones later. So the object A will have gravity. So there must be one gravity down. And the object A is in contact with the floor. So the floor must provide a normal force up. Okay, so I have those two. So I want you guys to help me add, are there any more? If so, what kind of force are we looking at? Any forces on A? Any more?
The contact
there's
of the book.
Contact with the book. So this other force will be pointing in which direction?
Down.
Downward, okay, downward. So how do I label it? This force is from who to who? From B to A, as John said in the chat. From B to A. So I have 2 down, 1 up. Are there any more? Now this one have 3 arrows down. So would that be one of them is C to A? Should I add one from C to A? Is there a force from C to A?
There's a force to C to B, which increases the force from B to A.
Yes, very good. You must be thinking that C must make an effect on A. It does, but it's not directly contacting. It's not directly acting on A. So we'll just stop right here. So just those 2 forces down, 1 up. And you make a very good point that the having C did influence on the force from B to A. So it is reflected, but not directly acting on A. So you only have those 2 forces down, one from the book B, one from gravity, the other force is up, that's from the floor. Okay, now let's draw, go ahead.
When you label the normal force on book A, that also includes the force that A exerts on B, right?
No, the force A exert on B should be drawn on B. I should draw that on B.
Oh, okay.
Yeah, very good. They're all related, but you don't draw them. So now let's draw the free body diagram for B and C. We did the A, let's draw the B and C. Okay, so let's draw the B. Okay, so we will draw forces on B. Okay, think about the B, isolate B. So in your mind, isolate and just focus your B. I'm gonna label the obvious one. I'm gonna label gravity force, gravity on B, of course. And you guys label other forces. Think about in which other forces it's in contact with. So B is touching C, okay? So the C, so there must be a force from C to B, always to B, because we're focused on B right now. And that force is pointing down or up?
Down.
So yeah, C is pushing B down. So if you can label, if you can put it together, you can put it together. Or if you want to draw them separately, you can just put it on the side. So another force from C to B, I'm gonna label like that. Okay, B is also touching A. So A is providing force on B, A to B, down or up?
Up.
Up. A to B. That's it, right? There's nothing more. That's those three forces. Let's do the C. So this is all the force on B. Now let's do all the forces on C. Okay, I will do the easy one. I'm gonna draw C. C, one down is gravity. Anything else on C? C is touching B. So B to C is providing a force up or down? Up, yes, up. F, C, sorry, B to C. You can see a force is acting on C is drawing on C separately. Force is acting on B is drawing on B separately, okay? All right, so now let's look at which of these are action-reaction pairs. I have another slide here I'm gonna point out as we're talking about this. So these are the forces you have already done. C, B, and A. Which of these are action-reaction pairs? Okay, so let's start with C. The normal force by B on C is up. At the same time, the force from C to B is down. So this one and this one are the action-reaction pairs, but they're acting on two different objects, one on C, one on B. They don't show up at the same free body diagram. Now, another force is a force by A on B is up, and the force by B on A is down. These two are action-reaction pairs, one on A and B separately. They all have the forces from the Earth. So at the same time, they all act on Earth actually. But you can see these forces barely make any influence on the Earth, right? Because of so small the mass compared with the Earth. But we are at the same time pulling on Earth, each one of us, because Earth is pulling us, attracting us, and we are attracting the Earth at the same time. So Earth is having these three forces. Each of them is an action-reaction pair of each of their weight. Of course, there must be a force that's so this force and the normal force by A on the floor is acting on the floor downward, but that is not drawn here. But that and this one is an action-reaction pair. So you can see it's on different objects. The action-reaction pair is always on different objects. So hopefully this example illustrates how do we carefully draw different forces and an action-reaction pair. All right, so let's look at this question. If you apply a net force F on either the heavy box M1 or the lighter box, now the effect of that, which one you touch the small one or you touch the big one, is that the two of them are moving together and accelerating. But what can we say about the contact force between these two boxes? Is it larger than case A or is it larger in case B? I will let you discuss this for a couple minutes within your individual group. All right. 10 more seconds if you haven't voted already. 10 more seconds to wrap up the vote. Okay, I'm gonna go ahead and close this and let's take a look. This is our results. I understand that maybe the question you might be thinking about, okay, are these action reaction pairs? But we actually have two different cases. We're not talking about the force is from one object to another and from 1 to 2 or 2 to 1. We're talking about the action reaction pair for two different situations. It seems like you're just pushing both of them, right? So how come that they may not be even be the same? Okay, so let's actually analyze the situation when by drawing free body diagram on each of them. For either of these cases, the same force is acting on M1 and M2 together, right? So do you agree that in here they have the acceleration and here they have the same kind of acceleration, right? Your same force on both of the objects, right? So same amount of force F on both of them. So they all have the same acceleration. So that is the first step. So acceleration in both cases is this F over the both of the masses. Now let's actually look at the contact force. Now, an easier way to look at the contact force, you can either look at on M1 or M2. I decided to look at an M1 because the contact force is the only force acting on one. So it's easier. I have only one force to consider. So the force from M2 to M1 is the only force acting on M1 in the horizontal direction. Normal force and gravity, those balance out in the Y, I don't want to consider. So that is a contact force we're talking about, right? The contact force we're talking about. So this force is responsible for accelerating M1 to such an acceleration. So we have calculated already M1 times F over M1 plus M2. So this is the contact force in this case. The contact force in the second case, you can see that M2 is a one here by itself, sort of with only one force acting on it. So I'm going to draw a free body diagram on 2 instead of 1. So M2. This force F M1 to M2 is again the contact force situation in this case. Okay, so how big is it? I'm applying Newton's second law on M2. This force is responsible for accelerating M2. So you have M2 times the same acceleration, right? So this is the same. But the mass is different. Mass 1 is bigger than M2, right? So that means this contact force in case 1 is bigger than the contact force in case 2, right? So it's going to be A, right? Contact force is actually bigger. So if you're thinking about action reaction pairs, then you need to draw the force on M2. Now, if I draw the force on M2 instead, M2 is here. I would do M2, you have a force, action reaction pair M1 to M2. So this and this are the action reaction pairs, right? But M2 also has this force directly in contact with M2, you have this F. Okay, so if you draw the free body diagram on M2, then you have two forces, right? One and the contact force together give you M2 times acceleration. You can solve your contact force that way as well, but focusing on M1 is easier. And here, case 2, focus on M2 is easier, right? So the answer is A. And you see that we actually have to work it out in using Newton's second law to figure out which one is bigger. Because if they were asking about action reaction pair, of course, these two are the same, but we're not comparing these two, we're comparing this force in case A and this force in case B, and they're different. Okay, so with a little bit time left, I would like to talk a little bit about the role of a centripetal force. So centripetal force, we mentioned it already with a barrel, rotating barrel, is named after its effect. for any kind of circular motion, you need a centripetal force that's pointing toward the center. Now, this force is named after its effect, and it's not really a new type of force. The forces, all the forces we talked about, gravity, normal force, tension, spring force, friction, are the forces we looked at. And the centripetal force is simply that role is played by some of these forces we talked about. So for example, let's look at some of the scenarios. If I have a rope, right? If I attach an object to one side of the rope and kind of rotate it, swing it on top of me in the horizontal direction. So I have a rope, attach an object, and I just simply swing it around, right? So the object is going in centripetal motion. So can you tell me in this case, what kind of force is playing the role of centripetal force? So all the forces we have are gravity, normal force, friction, tension, spring force. So if I attach a rope, an object to a rope and rotate it, which force do you think is providing the centripetal force in this case? Or acting like a centripetal force in this case? So this is a rope. In this case, the tension, yes, is acting like a centripetal force, right? Now, friction can be a centripetal force. Recall this example we talked about with the car, right? It's a friction between the tire and the surface is providing the centripetal force in this case. So we have a case for friction. With the person on the barrel, right? It's the normal force provided by the wall that is providing the centripetal force. You can see all of these, we can find examples for. Gravity, well, when you have the earth is moving around the sun, it's a centripetal motion, right? It's what we need a centripetal acceleration. So what force is providing that centripetal acceleration when we're talking about earth moving around the sun, rotating around the sun, or you can say the moon around the earth? What force is serving the role as the centripetal force? It is the gravity, universal gravity, gravitation between any massive objects. Any objects that has mass, you have gravity, okay? All right, so centripetal force is again not a new force. It's simply named after its effect. Sometimes a combination of these forces can serve as centripetal force, right? A combination of them. So let's look at an example. Here you have someone in a roller coaster. If I'm drawing a free body diagram of the person, no, actually the person along with the cart. So one thing, the cart at the top of the wheel of the track. What do you think the free body diagram will look like? And I will let you guys vote on this. Okay, last 10 more seconds. Haven't vote, please put in your vote. Okay, all right, I'm gonna go ahead and close this. Let's take a look at our results. This is the results. We pretty much split between B, C, and E. B, C, and E. Okay, so you might think it's quite confusing to think about the label these forces by thinking, okay, we have gravity and what else do we have? So there is a shortcut. The shortcut is think about what kind of motion the car is and think about in order to provide such an acceleration, in what direction should all your forces be pointing at. So this car is going in a circular motion. So for circular motion, you need centrifugal acceleration, right? You need centrifugal acceleration. So acceleration is pointing toward the center, right? So here in this case, when you're on top, in which way is the center? It's down, right? So you need a centrifugal acceleration pointing down. At this point, it must be this way. At this point, it must be this way. But at the top must be down. So that also means then all your forces, your net, all the forces on the cart must be adding up to provide in the same direction as your acceleration. So that means your F net must be down. Now, if you look at this diagram, if this is the case, your cart would be going up. Your cart would be bending away from your, gonna shoot upward because the force is upward. This is the same. You have a force bigger than the downward force. The car must accelerate upward. These two are canceling out. You will have no acceleration. These will give you an acceleration that's horizontally to the left. But our car we are going in the vertical direction right now. We're not going in the horizontal plane. So you can see using that method, we're able to rule out all of these choices, right? And the only one that's left that give us a net force down is C. And what are these two forces? So now we know this is correct. We can label these forces. We know that, okay, there must be gravity pointing down. And what is the other force? How do we call this?
Centripetal.
Huh? What's the other force? Now they add together.
Normal force.
Okay, the normal, yes, normal force from which object to the car? From which object? The car is in contact with the tracks. Yes, from the rail. Very good. From the rail or the tracks to the car. That's the normal force. Normal force and gravity together is your centrifugal force. Your centrifugal force is not new, right? It's simply a combination of these to have that effect. And remember, we at the beginning of the class, I said let's try to answer the question of how come you do not fall from a roller coaster? Well, you do not fall because we are in circular motion, right? The effect of such a centrifugal acceleration is to keep us in this motion, changing the direction of our velocities. It's not making us fall. Okay, and that's the answer. So centrifugal force is both normal force and gravity combined to provide a acceleration. And when you do fall, think about when you might fall, is when you start to lose contact with the track, then you will fall, right? If you're at close contact with the track, real tight together, that you have a big normal force, you're not gonna fall. But if your velocity is not big enough and you start to lose contact with your track, then you might going to fall. So when you barely make it over, barely is when your normal force goes to zero. And gravity is the only force to provide your centrifugal force. That is really actually not very safe. That's you're almost going to fall. You want your normal force to be big. But when you barely make it over the track, is your normal force go to zero. You no longer have that contact. You only have the gravity that's keeping you in the track. Okay. All right, so I do have a follow-up question on what's the bare minimum of speed to keep you to not lose contact with the loop. I have a solution here. I want you guys to go ahead and you can read that at home. Since you're already running out of time here, you just need to set your normal force to be 0 and let your gravity to be your centrifugal force, and you can calculate what is that speed. The higher the speed, the safer that you are. You're not going to fall. But if your speed is not big enough, then at this minimum speed, you can still barely make over, but if you any speed below that, you're going to fall. There isn't a force pushing the car against the track. Well, there is, but that force is acting on the track. You are pushing against the track, but that's acting on the track, not on the cart. We are drawing free body diagram on the track, on the cart. Just like with the barrel, rotating barrel, you feel like you've been thrown against the wall, and that force is acting on the wall, but not you, okay? All right, very good. Okay, so that's all for today. We finished our discussion for dynamics, Newton's third law. Starting Thursday, we will start work and energy, a new chapter, new topic. So everything we did from the beginning of the semester to the end of today will be the content on our first midterm, okay? All right, so I encourage you to come to office hours to ask questions in preparation for your exam. All right, I'll see you guys on Thursday.
Thank you.
Thank you, bye.
Bye,
Thank
Professor.
you.
Professor.
Bye, Professor. Have a good one.
Have a good
Thank
one.
you. Have a good day.
Have a good day. Bye, everybody.
Professor, I have a question.
Go ahead.
Okay, like for one of the assignments, I believe I have the right answer, but it's saying it's something else. Like for the, it's for the takeoff, and then for the 3 boxes, for question 3 of it, it's asking, well, like what's the net force of the box B? Is box B exerts on box A, and I put 24, and it says I'm like close, but like I don't know like what I'm doing wrong.
Okay. Let me look at it real quick. Is homework 4, is it?
Yeah, homework 4.
And it's called 3 blocks or 3 boxes?
Yeah, 3 boxes, my bad. Yeah, also 3 blocks too, but like I
Okay.
want to check.
What is the net force acting that box B exert on A? Oh, I think you might have just forgot the negative sign, because box on A is on the pointing to the left hand side.
Mm-hmm.
Yeah, I think that might be the only reason. You just need to add a negative sign.
Got it. I'm gonna type that in real quick. Yeah, it was a negative sign. So then that's probably the same thing I did for. Yeah, it's the negative sign. And then for the takeoff, I have a question for question 6. I got 50, the net force on the airplane as it levels off. I got 57,000.
So I do need to go now. So I want you to take a screenshot of your question and you email it to me, and I'll email you back with the answer.
Yeah, no worries. Thank you, Professor.
Send me a shoot me email. I'll get it to you today.
You got it. Thank you. Have a good rest of your day.
Thank you. You too.